Hi everybody, Physics Ninja. A couple years ago I did a very fun video on the precession of a bicycle wheel. I kind of spun this big gyroscope, this bicycle wheel, and I hung it up by a cable and I watched it precess. We described the motion of this precession using more qualitative arguments rather than quantitative. So today I want to go back and look at the precession of a gyroscope, but we're going to do it more mathematically in this case. Okay, we're also doing the experiments. I'm going to spin this gyroscope in two different directions, and then we're going to describe the precessional motion and derive an expression for the precessional frequency. So we have to be able to describe the angular momentum of a spinning gyroscope. We also have to look at the torque acting on the gyroscope and how both of those quantities get linked together. Okay, like with all my videos, if you like it, give it a thumbs up. Consider subscribing to my channel. It's the best way to support Physics Ninja. All right, let's get started. All right, let's first look at two experiments and then we'll come back and analyze the physics. All right, so in this first demonstration, what we're going to do is, I've got the gyroscope here wound up. And I'm going to pull on the string. If you can see as I pull on the string, if I look at it from the top down, it looks to me like it's rotating counterclockwise when I pull on the string. So let's see what happens now when I place it on this tiny little pivot here. All right, first let's try to get it on the first step. It's pretty tricky. All right, so it's spinning really fast. Notice that the gyroscope is precessing in this direction. It's okay, we get the hang of it. Okay, so let's have a look now at the other case, right? As I pull on the rope, you should see that the gyroscope, the wheel of the gyroscope here, is going to move like this, okay? As viewed from the top, this is in the clockwise direction. Pull on the rope. As viewed from the top, it moves in the clockwise direction. Notice the precessional direction now. All right, here is case one. Now, case one, I gave it a spin counterclockwise. So this is a side view of case one. And imagine I'm looking at the gyroscope, which is represented just by this disc here. If I give it a good spin omega, the way I've illustrated here, this would represent the counterclockwise direction. All right, I've listed this quantity here, d. That's the distance from the pivot to the center of gravity of that gyroscope. And I'm assuming that most of the mass here is in this disc region. If there is a mass, it means that there is a force of gravity acting on that spinning disc, and that force of gravity is straight down. The other force acting on the system is the normal force. That's acting on this other side here of the pivot. We call this the normal force. That's it. These are the two forces acting on the system. It doesn't get more complicated than that. Now, to really describe precessional motion and to describe torque, angular momentum, and all of these angular quantities, we really have to set up a proper coordinate system here just to describe all these vectors. All right, so here's the coordinate system that I'm going to use. Here's going to be the r hat direction. I'll call the direction up to be the z hat direction. And that means that the direction that's going into the page, I'll just describe like this, is what I call the theta hat direction. And theta basically just goes around that circle over here. All right, next thing I need to do is start describing some quantities like angular momentum and torque, and I need to define those things in 3 dimensions. So we're going to do it right here when I'm at this position. So let's kind of get rid of this figure here. Start with angular momentum. If I have a spinning object here, I have to know how to find the direction of this initial angular momentum when it is spinning at this angular frequency omega. Okay. And the way you do that is using this convention over here. This is called a right-hand rule. If I have a spinning object like this, I can describe the direction of the angular momentum of that object simply using the right-hand rule. You take your fingers and you put them in the direction of the rotation. So in this case, using your right hand, put your fingers in the direction of the rotation, and you should find that the angular momentum, at least the initial angular momentum of this disc or of the gyroscope, is pointing out of the disc like this. It's pointing to the right direction. Okay, so you should find that using this right-hand rule. So how can I now write it as a vector quantity? Well, again, we're simply going to apply our definition of a rigid object. The angular momentum, at least that initial angular momentum, would simply be the moment of inertia of that disk, which is I, multiplied by its angular velocity omega. And again, if it is initially pointing to the right, I'm going to call this r hat direction right here. All right, that is this initial angular momentum. Another quantity that I'm going to need now is, what is the torque acting on this system over here? Now, whenever you define a torque, you have to define a pivot somewhere, because torque is defined relative to a pivot. So I'm going to assume here that my pivot is right at this contact point. And this simplifies the torque because I don't have to worry about any torque being produced by the normal force because it's acting right at the pivot. Now, how do you find the torque? Now, remember, torque as a vector quantity is defined as, I'll use the letter tau, it's R cross F. Now, this is a cross product right here. So how would I do it for this particular case? And I'm looking at the torque produced by the weight. The weight is acting down, and R is pointing radially outward. So how would you do this? Well, the magnitude of R is simply D, right? So you have D in R hat cross with the force. So what's the force? The force is the weight, and it's acting down. So I'm going to call it minus mg, and that is in the z hat direction, right? The negative sign takes care of the fact that it's acting down. Okay, now how do I evaluate this cross product? Well, let's take out all the terms and stick some of those to the front. So you have minus d mg is the magnitude, and I'm still left with this cross product here of r cross z hat. So to find the direction of this cross product here, I'm going to use my rule. Again, it's another right-hand rule. You take your fingers, you point them along the first vector. In this case, what I'm going to do is I'm going to point them along the direction of minus r hat. Minus r hat is this direction right here. This is minus r hat. Okay, and I'm going to curl them toward the second vectors as illustrated by this. So if you curl your fingers now with your right hand, curl them toward this direction, what you should find is your thumb gives you the direction of that cross product. All right, so if I do that, my whole torque vector, you should find your thumb is pointing into the page. So what I have here, let me just change the order. I have M, G, D, and the vector that's pointing into the page, I've defined that as the theta hat direction. So this is what it looks like, theta hat. All right, so that is the direction of the torque at that particular instant. So I have my initial angular momentum, which is equation 1, and now I have my torque direction into the page. All right, let's now plot it from the top-down view, and then we'll be able to analyze this and introduce our equation of motion. All right, it now helps to just plot some of these vectors in order just to get a better understanding of what's going on. Now I'm going to plot it in the side view and also the top-down view. So we've already got our initial angular momentum vector pointing in the r hat direction in the side view. Let's now add the torque equation, the torque direction. It is pointing in the theta hat, and that is going into the page. So that means from the side view, I should have a torque that looks like this. All right, what about from the top-down view? The top-down view, the coordinate system looks a little bit different. It's still r hat here. I'm looking from up above down below, so I see that the normal is pointing out of the page. Now the z direction is out of the page, and theta hat now is pointing upward if it is a top-down view. Now you may have to think about this for a while. If I go ahead now and draw the torque vector now should look something like this. It's in the theta hat direction. So this is the total torque acting on the system. So if you think about both of those vectors now, at least from the top-down image, this is what we have. We have a torque vector which is in this direction, and we had an initial angular momentum which is in this direction. All right, now we have to apply the equation of motion in order to understand the precessional motion. And I'm going to focus on the top-down image. It's going to be easier to plot all of these vectors. All right, let's go on the next page and look at the dynamics now associated with the precession. All right, so we have our top-down figure over here with my initial angular momentum, which was only due to the spinning gyroscope. So we had that vector that is pointing out. And we had the torque that is in the theta hat direction. Now, if you think about the precessional motion, okay, we're going to do something here called the precessional approximation. Because when we apply our torque equation of motion, okay, think about it. The angular momentum really has two components. It has the spinning part, which is going to be our dominant angular momentum. But once everything starts moving like this, we have mass that is spinning about an axis, right? Think about the center of mass of this gyroscope that's rotating around. That also has angular momentum, okay? We are actually going to neglect that entire term. Okay, we're going to assume that it's small, and from the experiment, it's probably a pretty valid approximation because it was rotating pretty slow, and compared to the angular momentum of the spin, we're assuming it's a small quantity. Okay, so that's an important approximation called the precessional approximation. All right, let's look at our equation of motion now. All right, so now we write down our torque equation. The torque acting on the system is the change of the total angular momentum with respect to time. And again, I said the total was broken down into two components. It was the spin plus the center of mass component, right? Rotating around that axis. In that precessional approximation, we are neglecting the center of mass and only considering how the spin angular momentum changes with respect to time. Okay, so that is going to be our, we call this the precessional approximation. Okay, so let's simplify that. This is a torque equation, vector equation, I mean. All right, so torque is the rate of change of the spin part with respect to time. Well, that's great because initially all we had was spin. So let me bring the delta t on the other side. Torque multiplied by some small amount of time equals the change of the angular momentum. I'll drop the spin now. I think we know we're talking about spin. So remember what a delta L is. It's always a final value minus an initial value. And what if I was just worried about the magnitude of this equation, right? If you were just worried about the magnitude, you can write that the magnitude of the torque multiplied by the time is equal to the magnitude of the change in angular momentum. All right, let's add some vectors to our figure now. We have that initial angular momentum. We had that our torque was in this direction. Well, that must also be the direction of torque multiplied by delta t. So this is torque multiplied by delta t. Guess what? The vector that is left over, that goes over here, this has to be my L final. This is my L final. Now, a couple things about this torque and that initial angular momentum. They were perpendicular to each other. Okay? At every instant in time, we're always going to find this using this precessional approximation. The torque is always perpendicular to the instantaneous angular momentum. This is really, really important. So guess what that means? It means that the angular momentum only changes the direction. The magnitude doesn't change. So let me go ahead now, and in this figure, we're going to introduce, what is this angle? How much angle do I sweep out in a small amount of time, delta t? Remember, this green vector is also equal to the change in angular momentum. Okay, so we should be able to write an expression now for how long is this vector over here that links two vectors, right? Remember, this guy is simply delta L. It's equal to torque multiplied by delta t. All right, we should be able to write that distance, or that difference between the two vectors, the magnitude, has to be equal to the length multiplied by that tiny angle delta phi. Okay? If you're not sure about this, consider any circle, right? If you consider any circle and you want to find what is this arc length right here, well, you have a radius r, and here you have some angle delta phi, right? My arc length over on this side would be what? Well, you'd write the arc length is simply equal to the radius multiplied by that angle. Okay, we know that from simple geometry. So we have a similar picture here in terms of angular momentum. We have angular momentum. Angular momentum, we're assuming it doesn't change because the torque is perpendicular to the vector. And this is the change in length, the change in angular momentum. All right, so you should be able to write this expression down, which is completely analogous to finding the arc length of a circle. Now what do? We go back to our expression over here. Let's go back to our torque equation. Okay, so it says that the torque, well, let's go ahead and substitute our value for the magnitude of the torque. Let's look at our magnitudes over here. The magnitude of the torque multiplied by delta t has to be equal to the magnitude of delta L. That's L delta phi. Okay? The magnitude of the torque we can get from our expression over here. It's simply mgd multiplied by delta t equals L delta phi. Okay? Let's bring the delta t down on the other side. All right, so we get, if we do that, we get m dg. Angular momentum magnitude doesn't change, and now we're left with this rate of change of this angle phi with respect to time. Okay, this guy right here is what we are going to call uppercase omega. And this is what I am calling now this precessional angular velocity. Remember, it's telling me how this angle is changing with respect to time. Right? d phi dt is this precessional angular velocity. Again, my precessional approximation now, if I go back, is basically saying that my omega has to be much, much bigger than this precessional angular velocity. So let's go ahead now. We can write our final expression. Right? If you introduce that precessional angular velocity, we're going to get that precessional angular velocity is equal to mgd, and I can bring the angular momentum downstairs, L over here. Now, if I can write this slightly differently here, let me just kind of make some room. I can also substitute what the magnitude of that angular velocity is. It's mgd divided by, remember, that magnitude of the angular momentum is the moment of inertia of this gyroscope multiplied by that spin angular frequency, omega, lowercase omega in this case. All right, so this is what my expression says. Now let's have a look at some limiting cases. All right, it says if you spin it really, really fast, right? If you spin something really, really fast, you make omega big, right? Omega big means that my precessional angular velocity is going to be a smaller value. Okay, there's other dependence here on the mass, on the distance to the pivot, and also on the moment of inertia of that gyroscope. But if I just look at that spin dependence, that's what it tells me. Okay, all right, let's go have a look now at if I make that spin in the opposite direction. Let's draw out the top-down view and look at the vectors again. All right, here's case 2 again. Case 2, I was spinning it in the opposite direction, right? So if you're looking at it again from this side, it appears to be rotating in the clockwise direction. So again, if you use your right-hand rule, you put your fingers along the spin direction, this gives you the direction of that angular momentum, initially of that disk. Now the torque hasn't changed, right? Our torque vector is still the weight-producing torque, so the torque is still into the page. The only thing that's changed now is this direction. So let's go ahead now and plot the vectors. And again, those vectors are free to move around, right? Here I can plot my angular momentum vector like this. And all I know now is that my torque is going into the page. Well, that means that the torque multiplied by delta t is in this direction. Okay? We proceed using the exact same arguments that we did. That means what's left, this vector right here, again, using this precessional approximation, this is my final angular velocity, and you can see it traces out some angle delta phi. Now you proceed with the exact same analysis, and what you find now is that the precessional difference Again, this is a top-down view of the vectors, but the precessional direction now would also be in the clockwise direction. It would be exactly the opposite of what we just did. We would find that my precessional angular velocity is still mdg divided by I omega. Okay, that hasn't changed. Only the direction will change if I change the spin direction. All right, now you go back and you look at the experiment. Let's zoom in a little bit so we can see what's going on. We can use our hands to describe the direction of the vectors and have a look at the experiment now. Hopefully you could see that the spin is really, really fast. Look at the precessional direction and look at the precessional, how fast it's precessing. It's really slow compared to the spin. All right, hopefully the equation now makes sense to you why it has that general form. All right, let's go look at that experiment again.
All right, so in our first case here, I'm going to spin it here. I'm going to pull on the string, and you're going to see that it's going to rotate as viewed from this perspective here. It's going to start rotating in this direction here. As I view it from the top of the gyroscope, it looks like to me it's going to rotate in the counterclockwise direction when I pull on the string. Let me wind it back up. So that means that it's going to create an angular momentum. You take your right hand, you put it in the direction of the rotation, and my thumb gives me the direction of that angular momentum. So the angular momentum is going to be pointing away from this axis of the gyroscope. Now we're going to place it on this pivot once it's spinning really fast, and let's see what happens. Oh, I actually got to place it on the pivot here. So we notice here that it's precessing here counterclockwise as viewed from the top. Oh, pretty cool. Eventually it slows down because of the friction. But that's pretty cool. All right, let's have a look now. What would happen if I spin it in the opposite direction? Right? What if that initial spin is in the opposite direction? What's going to happen to the precession of this gyroscope? Put the string back in here. All right, so now I want to give it a spin such that opposite direction. All right, let's just put the rope here around this main axle and watch what happens. All right, so again, as viewed from the camera or from the top. Now, when I pull on the string, now it's spinning. As viewed from the top, it's spinning clockwise. So again, if you think about the direction of the angular momentum in this case, the direction of the angular momentum, I take my fingers along that spin direction, and my thumb is pointing in this direction, going down in this case. That's the direction of the angular momentum in this case. Now let's have a look at what happens when I place the spinning gyroscope on this pivot point over here. As viewed from the top now, we get precession that is in the clockwise direction. And then it eventually falls off just due to the friction.